Good day everyone. I am Atukora LAKS E20 A final year project titled under the framework for real-time HVAC parameter estimation using extended Kalman filtering with the assistant modeling. The research is conducted under supervision of Dr. DHS Maitriba. So this is the previous outline for the presentation. HVAC systems alone account for 10% of global building energy consumption, and IEA expect this demand to double by 2050. Therefore, efficient building energy modeling is essential for analyzing and optimizing the HVAC performance. With recent advances in AI assisted engineering workflows, these traditional building energy modeling tasks can now be performed more efficiently and systematically. So, through a comprehensive literature review, these research gaps were identified. First one, mathematically difficult to model building parameters. Key parameters such as effective thermal capacitance, envelope conductors, infiltration, and occupancy are difficult to calculate using the first principles. Second one, indirect occupancy estimation limitations. The real-time occupancy estimation using CO2 dynamics remains unexplored in practical building energy modeling frameworks. Next one, separated treatment of thermal comfort and indoor air quality. The thermal comfort and indoor air quality are often handled independently. Fourth gap, limited parameter identifiability studies. Building energy parameters are often assumed constant with limited investigation observability under real-world operating conditions. Final one, fifth one, complexity of high-fidelity building energy workflows. Energy plus based modeling remains complex and difficult to deploy efficiently. So this will be the proposed innovative method. One, AI-assisted modeling pipeline. This addresses the building energy model workflow complexity gap by automating IDF generation. IDF is the energy plus core file where I describe the building and reducing the modeling effort. Second one, augmented state external Kalman field estimation. This addresses the mathematically difficult to model building parameters estimated using the Kalman method. Third one, CO2 based occupancy sensing. Address the indirect occupancy estimation gap by leveraging the CO2 dynamics instead of solely depend on counting the occupancy. Fourth one, solution unified web-based dashboard. This centralized the model generation, simulation, control, and analyze estimation all in a single place. So feasibility analysis. This project contains two parts mainly: web UI and the experimental setup. So the web UI is as shown here. So you can see here this entire web interface was developed for this final year project. This serves as a unified place for configure energy plus IDF generation using LLM visualization of the result in a single place. First here we can go to the simulation setup. So first, since we are using large language models to generate the IDF, we can first check the connection, backend connection with those models. Now, once connection is successful, we can describe the building in our natural language. Here, I will just use a simple explanation. So then we can set the simulation settings for the, we can simulate for a day or entire year. Then we can set the weather location based on what we select here. The energy backend will auto select the appropriate EPW weather files to simulate the simulation. Then we can set our LLM model to generate the IDF file. Then we can give the simulation. So once we go to the result, we can show here the status is running. So our simulation is the LLM is generating. So we can go to the collab backend. This is where all the energy plus calculation, Kalman filter, and every calculation will be happen. So as you can see here, now the IDF is generating by the OpenAI LLM. Once the IDF generated, as you can see here, energy plus simulation will be run. It will be run using library called E plus util, which was developed by Dr. DHS Maitripala. Finally, once the energy plus is run and the simulation is done, we can come back to the front end, and you can see here now the status has changed to the done. Once we can click here, we can see the generated IDF. You can see here those ones highlighted in the green are the ones the LLM is generated based on our uh, user input given in the front end. If we didn't have that, we have to set up this each and every single setting manually, which is a tedious process because of the this is text-based file. If we given in detail description like sizes of the building and the window sizes, example, we can get a more described completed IDF file here. To validate the this framework physically, precision multi-zone testing has been decided. As you can see here, two zones will be used, and the inflow and return will be used as the existing thermal HU setup, and this model will be separate. This will be created separately. So this consists two main systems: sensing system where the sensors for the reading, which used for the Kalman calculation and other processes, and another system is for the artificial environment simulation. So for that, to simulate the heat generation of people, bulbs and heat generation devices will be used. And for the CO2 simulation, a CO2 injection system will be developed, and those will be created through a controller separately to create the randomization. And sensors will also be controlled by a controller. A summary of the testing is here. For the controller, ESP32 will be used. So the 32 the controller will uh, open a streamline of sensoring data, and then user laptop can be subscribed to the that data stream, and then those stream will be used for the developed web UI for the calculation. This is a proposed project plan. So now literature review and problem formulation, feasibility analysis is done, and the web UI is successfully delivered and in a working prototype. The AI based LLM IDF generation foundation work is carried out, and so the next immediate step involves scaling this LLM generation to the full level single zone scenario where we can describe the zone in detail. So this will conclude my presentation. Thank you.